All right, so we've got this example, and we want to look at finding our path of length 3. It doesn't say find the path of length 3, it just says find a path of length 3. So I'll let you guys see if you can spot one. Anybody spot a path of length 3 in this graph? You can find it both off the ordered pairs or off the picture. Personally, I think finding it off the diagram is easiest, but that's a personal opinion. So what do you think? Anybody spot a length 3 path? Now note, when you're looking for a length 3 path, there's a couple things you have to consider. The first is knowing what length 3 means. Does anybody remember what length 3 means with respect to paths? Well, I guess even more foundational, what is a path? Ooh, you've got something that works as a beautiful path. It is, however, not length 3. So yes, you could go from 1 to 2 to 3, and that is a perfectly lovely path. It is, however, length 2. So, and that's somebody that we're going to look down here because R2 is the set of all length 2 paths. Now, if I say that this guy, let me go ahead and write down what you actually have. How you'd write it down is like a little baby sequence. If I say that guy is length 2, what was I counting to get 2? That works, yeah. I think of it as in terms of counting the edges or counting the arrows, but yeah, you could totally think of it as counting each of the changes in the numbers as well, or the number of ordered pairs you had to use to progress from one of those numbers in set A to another number in set A. It's one of the reasons why I think it's easier to find paths and also cycles when you come back to where you started in the actual diagram in the picture over there, just because those changes, those relations, those ordered pairs are represented by an edge, and it's easy to count the edges. So here, where'd we go? 1, 2, length 2. Now, if we wanted to bump this up to a length 3 path, once we progress, and actually let me highlight this. So right now, we start at 1, we traveled to 2, we traveled to 3, so there's our length 2. What can we do to bump this up to a length 3 path? What should we do next? There you go. Just travel or use one more edge, and that will bump us up into a length 3 path. Now, quick check, because this is where it messes with people's heads. If you look at what we just wrote for the name of that length 3 path, I labeled it with a pi because it's standard to do lowercase Greek letters for the name of your path. When we have the numbers there that came from our building set A, we just had 1, 2, 3, 4. Very nice, straightforward length 3 path. How many numbers do you see in that list? Or finite sequence? Yep. It turns out with a path, there's always one more number in the name of the path, or the description of the path, or that finite sequence that corresponds to the path than the actual length of the path. So if you have, if here you have n numbers, the thing is going to be length n minus 1. And that's just how vertices, endpoints of these directed edges work. Notice if you have one directed edge or one arrow right here, you're going to have 2 endpoints. Turns out there's always one more of those guys than there are the actual relations or the edges. Okay, just as a heads up. Now, that's background. The second thing that we want to do in here is we want to calculate R2. R2 is another relation, so at the end of the day, it would be a set of ordered pairs, and specifically, each of those ordered pairs corresponds to a length 2 path. So step 1 is you have to find all your length 2 paths. So if we wanted to calculate all of our length 2 paths in this particular graph, well, there's a lot of different ways to do it, but if you want to make sure you don't miss any, here's one of the things that I would need to worry about. But a question came in. So there is a distinction, and let me actually, where's a good spot to put that distinction? How about over here to the side? So a path, specifically, you're going to start and end in 2 different places. That's the key thing with the path. Now, in terms of a cycle is a path, that comes back to the starting point. Now, in terms of the length is actually computed the same way for both of them. Okay. So the length of this path right here would be 2 because we used 2 of these directed edges, or 2 of the ordered pairs were involved. For the cycle, we would use 3. Why? Because we used 3 arrows or 3 of those ordered pairs from the relation. Okay. So it depends on what you need. If you're specifically talking about a path, that normally excludes the case where you come back to your starting point, and that's the big distinction between those two words of the path and the cycle. Now, in terms of what we're about to do with R2, I'm going to be a little bit loose with the words path and cycle. Officially, if you were dealing with graphs, not necessarily starting with a relation, but only starting with the graphs, the definition of a path is you're not allowed to repeat vertices, you're not allowed to repeat edges. Same deal with a cycle, you're not allowed to repeat vertices or edges. The only exception is you go back to the same vertex you started with. In terms of our course, though, all of our paths and cycles, at least for right now, are going to be coming from relations. And what we're doing with relations is we're going to ignore those criteria where we're going to be able to go back and reuse vertices if we need to, reuse edges if we need to, because really, instead of the paths and the cycles, we're using something called here, walks. And down here, it actually doesn't have a corresponding name. So we're just going to do a base case name here, and we're going to be a little bit loose with our definitions. Okay. Now, in terms with R2, we want all of our length 2 paths. And when we say this, we're actually, in this case with R2, I'm telling you it's length 2 paths, but in reality, what it is using 2 edges, starting at some vertex and using 2 edges to get somewhere else in the graph. And for this guy, we don't care if it's a path, we don't care if it's a cycle, we don't care if it's reusing the same vertices a bazillion times. All we care about is where can we travel using 2 edges. So let me actually be slightly more precise here. So this guy here is, where can we go with 2 of our directed edges? Directed just meaning those arrows. Okay. It's easier to say all your length 2 paths, but it's actually a little bit more than that. So if we tried to make a chart of what we were doing, suppose we started at, so here's our starting point. Suppose we started, actually I really didn't want to use the word started, but oh well. Suppose we started at vertex 1. Where could we go in 1 step, or using 1 edge if we start at vertex 1? Where could we travel to, in other words? And I'm totally shouting this out to you guys, so see if you can spot it in the graph. Or if you prefer, in the ordered pairs. Hint, your answers will be the integers 1 through 6, or some selection thereof. Yep, you could totally get to 2. Could you get anywhere other than 2? You could also get to 6, and those are the only 2 cases. Now, we wanted where you could go with 2 edges. So once we get to 1, then 2, we need to travel along 1 more edge. So if you then go 1 to 2, where could you go once you were at 2? And remember, you have to travel along the edge in the same direction as the edge. Yep, you could only go to 3 because there's only 1 edge here, leaving 2. And since we only wanted to travel 2 edges, or trying to build our length 2 paths, quote unquote, plus, we'll stop here. So this would be where we end. Now, if we'd gone the other direction, if we traveled down to vertex 6 here, where would we go if we wanted to get into a length 2 path, if we wanted to use 1 more edge? So we're now at 6. Yep, totally come back here to 2, and that's also the only option. So notice if you started at 1, you actually have 2 length 2 paths, 1, 2, 3, or 1, 6, 2. Both of them are totally viable and perfectly fine to use. Now, that's it if you started at vertex 1. But maybe you then started at vertex 2, and I'm going to put a line here to separate. So if we started at vertex 2, where could we go next in one step? Yep, you can only go here to vertex 3. Now, once you're at vertex 3, where can you go? And here is where you might not necessarily get a proper path. You just want to travel along 2 edges. So once you're at 3, let me wiggle the cursor so we can see it. Once we're here at 3, where could we go next for our second edge? Yep, 4 totally works. And 2 to 3 to 4 is a proper length 2 path. There is, however, another option. Anybody spot the other option? Actually, there's several more options. You could also stay at 3. You could take this little loop. That, technically speaking, so you could go here to 3. As soon as you grab this loop, so you've used 2 vertices in a row, that's where I said these are paths plus. The plus there is some guys that aren't technically paths, but we still need them for R2. When you repeat a vertex, technically speaking, it's not considered a path anymore. However, we're going to need it in our particular case to get all of our options. And yes, you could also go back to 2. And if you go back to 2, notice 2 is where we started at. Technically, that's a length 2 cycle, okay, where you go 2 to 3, then back to 2. Okay, so here there are 3 different ways that we could travel along 2 edges. One a proper path, one a proper cycle, and one that's just using 2 edges and is technically called a walk. And that's all the places where you can go if you started at vertex 2. Now, notice what we're doing in terms of this strategy. We're trying to be strategic here. And yes, this would be something where we'd need to do this for every single one of the numbers in your building set. In other words, every single one of these vertices. Now, I'm going to show you a shortcut after we finish with this example on how you can get R2 a whole lot quicker, okay? Because notice, this is a relatively small picture right here, and this is going to take a little while. Now, if we weren't talking it out together and you knew what you were doing, it would be a whole lot quicker. Okay? Typically, when we talk out examples in class, they have a tendency to be at least twice to 5 times longer than what it would actually take you to do on your own. Again, assumption is that you knew what you're doing. If you get stuck, that's not necessarily true. All right, so if we start at vertex 3, where could we go in one step? So with one edge. Yep. We could go to 4, we could go to 3, or we could go to 2, and then we have to figure out what we're going to do with those at those 3 new vertices. Now, the easy one is if you take this little loop and you stay at 3, well, you have the same 3 options. You could go to 4, you could stay at 3, or you could go back to 2. Okay? Now, what happens if at 3 you go to 4? So getting that first one we skipped. So start at 3, go to 4. Where can we go next to pick up the next edge? We could go out to 6, and that's the only option there. Now, what happens if we started at 3, and instead of staying at 3 or going to 4, we went to 2? So we traveled on this guy here that's not highlighted. Where would we go once we're at 2? The only option is we'd have to go back to 3 because the out degree of 2 is 1. Okay? Perfect. Now, what happens if we start at 4? So at 4, you'd have to go to 6 because the out degree of 4 is 1. Notice the options that you have at each stage are totally based on the out degree of your vertex. So 4 to 6, and once you're at 6, where do you have to go? There's only one option, you'd have to go to 2. And I on purpose put that one option there, the only length 2 path starting at 4 down at the very bottom of the screen there, simply because I want a little bit of space here where we can actually write out what R2 is. All right. Now, if we start at 5, what can we do if we start at 5? If we start at 5, you're going to have to go to 3. It's the only option. And once you're at 3, it's the same choices that we've had before. We could go to 4, we could stay at 3, or we could go to 2, and those are your only options. Now, what about 6? Only option for 6 is you have to go to 2. Now, once you're at 2, where can you go? And the only option of 6 to 2, you have to here go to 3 because there's only one out. The out degree of 2 is 1, so that's the only length 2 path of 6. And if you notice these, most of these are actual length 2 paths. So 6, 2, 3, that's an actual length 2 path. 5, 3, 4, that's a length 2 path. 5, 3, 2, that's a length 2 path. 5, 3, 3 is not technically a path, but it still uses 2 edges. 4, 6, 2, length 2 path, etc. Now, let's put this all together. So if you wanted to figure out R2 takes all of that information that we just did in this chart form and compiles it. So R2 talks about where you can get in 2 steps, or using 2 of your directed edges, using 2 of your arrows, or using 2 of your ordered pairs. You can think about it in all of those ways, and all of those ways would be correct. Okay? So if you started at 1, where can you end up? Note what we're going to do. Starting at 1, we're ignoring the middle guys. They were only there for scratch work, and it's where do we end after 2 steps. So we can start at 1, and we can end at either 2, or we can end at 3. And I just made that numerically in order. And those are the only options in terms of where we could start at 1 and where we can end. Now, if we then looked at 2, we can start at 2 and we could end at 3 different places, 2, 3, or 4. This is 2, 3, 4. And I'm going to have you guys tell me what to do for starting at 3. So what do you guys think? If we start at 3, what should be the ordered pairs where we start at 3? We could end at 6, yep. What's another ending point for us? 4, grabbing the 4 right here. Now go ahead and do all 3 of these guys. You also have 3, 3, and you also have 3, 2. Now, have we picked up all of the ending points that we get if we start at 3? So here's 3. Did we pick up all of these guys? Because we don't have 5 ordered pairs right here. And the answer is yes. You're not going to do the duplicated guy. You're not actually going to put 2 copies of 3, 3. Why? Because remember, this is really a set. What do you do with sets? You don't write down the duplicated items. So what it means when you have the duplicates, it means there's 2 different ways to start at 3 and end at 3. So there's 2 different, for lack of a better term right now, 2 different paths that start and end at 3. However, in terms of R2, because we're writing out the set and we don't care about the middle, we don't care about how you got there, we just want to know if you got to that ending point, you're only going to put the 1 copy. Okay, so that's one of the reasons I wanted to make sure to write out all of this stuff. Everything else is straightforward. So like if you started at 4, this would be 4, 2. If you started at 5, your ends would be the 4, 3, and 2. I'll just put them in numerical order. So 5, 2, 5, 3, 5, 4. And the last one that starts at 6 would be 6, 3. Okay. And this method that we just did, this will work for any not direct graph. This will work for any relation to build your R2. There is, however, a shortcut. Now, I forgot what you guys said. I think you guys said last time about half of you have done linear algebra. Roughly speaking, correct? All right, so it turns out if you are comfortable with matrices, or if you have a calculator that you're comfortable plugging this into a calculator, you can do this with the matrix related to your guy right here. And we'll do that in a future example, but let me show you what the actual formula is. And then we'll go over how to do that in one of our future examples. If you take the matrix associated with your relation and you square it, You will not get the matrix associated with this guy, but it's close. Remember, the original matrix associated with your relation is a Boolean matrix, meaning all of the entries are ones and zeros. When you square the thing, what you'll get is any one of these lengths 2, for lack of a better word, paths. You'll get a 1 for all of these guys, but notice here we had 2 ways of getting from 3 to 3. You would actually get a 2 in this slot. It'll tell you how many ways there are to get from vertex 3 to vertex 4. In our case, there's 1, so this would correspond to a 1 in the new matrix. This one, there's 2, so there'd be a 2 here. So what you would look for in terms of finding R2 is you square the matrix. So this would be like a step 1. And then the actual matrix that you look at, the guy that you want, would be all non-zeros or non-zero entries from that squared matrix above convert to 1s. Leave the zeros alone. Okay? And that's how to find the matrix representation of R2. Now, if all you want are the ordered pairs, you can actually just pull all of the entries from this guy that aren't 0, and all of those non-zero entries from your square matrix, your matrix squared right here, would actually turn into your ordered pairs. Now, notice what I skipped out on. I skipped out on actually saying the calculations and how to square a matrix. So when we go over an example in the future of actually applying this method or this algorithm or this technique to find your R2, well, I'll actually pull us out and we'll do a little baby example of how to actually multiply your matrices together to square a matrix. And I have that set up on an example that's smaller. That way I don't have to deal with a 6 by 6 matrix. You can also put this into a calculator. If you have, what is it? I know all the TI 83s, 84s, 89s, etc. have it where you can enter in your matrix into your calculator, and then you just pull the symbol for your matrix and put a little exponent of 2 on it, and it'll automatically square it for you too. Okay? We're not a linear algebra class. I don't care if you use a calculator to square your matrix all the time. Okay. All right. That being said, this is the crash course in what R2 is, and like I said, I'll show you that method in a little bit. It'll actually come into play. We need R2 when we talk about our last property of transitivity. That is a good question. So the question was, why didn't we write down 1/6 inside of R2? And the reason for that is when we were writing down all of these different guys, and let me actually highlight, I probably should have done that earlier. Yellow's okay. The starting point, or the first position, is here. In R2, this 2 right here represents that you've used 2 edges, so you're only going to be looking at those guys right there. In other words, you completely ignore the middle parts. Notice what you also do. This is not a copy of the original relation. The only thing that we used the original relation for was the actual, how we got these arrows, how we got these relationships in this chart. The new guy actually, so here's a fun part, R2 sometimes looks absolutely nothing whatsoever like the original relation other than the fact it's from the same building set. Sometimes it looks identically the same. Sometimes it looks like a subset. In our case, some of them are the same and some of them are very much different. Right, but that would be the idea, is you are actually not dealing with these middle guys. You're only from this chart of all of your, for lack of a better word, length 2 paths. You're only grabbing your starting point and your stopping point of those like 2 guys. Hopefully that cleared that up. Other questions? Make sense how we built this R2 relation from all of the work that we did. Okay, so you're good. Other questions? Because we're about to put this on a back burner and go look at something else real quick. I should say real quick, we're going to need this again, but it'll be on our last property that we deal with. So either end of today or beginning of next time. All right, so I'm seeing no other questions come in from you guys. So the next thing that we've got is I'm going to throw something that's similar-esque to this to you guys to look over it. But first, before we actually go into our next thing, I need to give you some directions because it's a little bit different than our normal activities. So there's no need for us to record this. So the first property of relation is something called reflexive. And I'm going to start off and give you guys the really, really formal version of this property, which is all rooted back in the actual ordered pairs of the relation. So what this says here is you got some relation R, it's on your set A, so notice what this means. Find my little cursor. This means that R is a subset of A cross A. So both of the two ordered pairs are coming from this building set A. It's going to be reflexive if A is related to A for all elements A in your building set A. Now, what does this mean? I'm going to put it in the three ways that we represent our relation. First thing it means is all of your ordered, don't write a B, just a second, I need to erase that. All of your ordered pairs, A comma A, are inside of your relation. And this is for all A. Okay? So that's in the relation as ordered pairs. Now, what does this mean in terms of your digraph? In terms of the graphical representation, this means that you have loops on all the vertices. So all the possible loops are involved in your digraph. And if you were in the matrix representation, anybody have a guess what it would mean in terms of the matrix? Ooh, no guesses coming through. So if you have 1 in your set A, 1 comma 1 would have to be in the relation. So that would correspond to the first position. It turns out A comma A for all of your elements A is if you look along the diagonal of the matrix, so that's coming at this upper left corner down to the lower right corner, all these guys, all those entries are all 1s. It doesn't matter what any of the other entries in the matrix are, 1s, 0s, whatever. If you're a reflexive relation along that main diagonal right there, you'll have all 1s. So that's one of the ways that you can identify. So these are the 3 ways you can identify reflexive if you have those 3 different situations. And if you just have a formula, you'd have to check the formula. Now, the property that is almost always talked about along the same lines as reflexive is somebody called irreflexive. If you know anything about the beginning parts of words, if you have IR in front of a word, it basically means not. So this is not just not reflexive, it's the extreme part of not reflexive. So this is some relation R on some building set A. Again, it has to be a subset of A cross A, so both the first and the second coordinates are coming from this building set A. You're going to tag it as having the property irreflexive if A is never related to A for all of your little elements inside of the set A, inside the building set A. So notice what that means here. In terms of your actual relation with ordered pairs, you would have that A comma A is never, and I did the wrong symbol, is never in the relation. So let me go ahead and, well, that is awkward. Come, stop doing that. We'll go ahead and erase that thing. I think the issue with those weird flips is my mouse. The scrolling bit on my mouse is actually really nice. It's a touchscreen scroller, but I think when I accidentally touch it, that's what's going on with the PowerPoint here. Now, in terms of your digraph representation, what happens? Here you have no loops. So on every single one of your vertices in this graphical representation, in this digraph representation, what happens? No loops whatsoever, okay? Now, thirdly, what happens with your matrix? Any guesses what's going to happen with the matrix? Well, the A comma A is dealing with your diagonal. It's all those guys that upper left corner all the way stacked down to lower right corner. So here what happens, well, if you have none of the A comma A relations in your relationships inside your relation, this here wouldn't be all ones like reflexive. Instead, it would be all zeros. So those are the two extreme cases, the reflexive and irreflexive. In terms of where we're going with relations, we're definitely going to want the property of reflexive, but in terms of drawing them, having the irreflexive property has no loops on it, and it looks sometimes easier. Okay. However, there's actually a third case you can have. Anybody have a guess on what the third case you could have would be for any old graph? So comment at the end here. We could actually have the situation not reflexive and not irreflexive. Anybody have a guess how you could tell if somebody was both not reflexive and not irreflexive? In other words, what would you have? Anybody have a guess how you could be neither reflexive nor irreflexive? As this is a really, really common thing. In actuality, all of your guys' graphs that you played around with in activity and the activity we just had were both not reflexive as well as not irreflexive. Yeah. So if you were looking in your matrix, you would have at least 1, 1 and at least 1, 0. So having a mixture of ones and zeros along that diagonal would totally be a way to spot it in the matrix. Where's my cursor? It's coming. There it is, right here. In the digraph, this would be where you have at least one loop, but not all of the vertices have loops. And over here, you have some of your doubled up ordered pairs, but not all of them if they were written out in ordered pairs. Okay. In other words, you have a mixture, not the one, not all, but also not none. Okay. So let's look at an example. An example that I've got here is this guy, which is, suppose you have the building set of the integers 1 through 4. And I went ahead and just wrote out the ordered pairs right here of 1, 1, 1, 3, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, and 4, 4. So if we looked at both the properties of reflexive and irreflexive, what do you think? Is this relationship reflexive? Let's start with reflexive. Yep. So it turns out that, yep, this guy is reflexive. How do you know? You've got the ordered pair 1, 1, 2, 2, 3, 3, and 4, 4. And notice you have to make sure you have the ordered pairs for each of your building sets elements. So here our building sets elements were 1, 2, 3, and 4. So we had to have these 4 ordered pairs of the 1, 1, 2, 2, 3, 3, and 4, 4. Now, if you've just found that your relationship is reflexive, any guesses what the answer would be here for whether this guy has the irreflexive property or is irreflexive? So what do we think? Is this example irreflexive? And to remind ourselves, in the corner, I'll put the definition. Shorthand version of the definition. Reflexive, shorthand version of the definition is? And shorthand definition of irreflexive is this. So what do you guys think? Is that same example also irreflexive? Hint, the answer is yes or no. It's a 50-50 shot. Correct. So this one actually is not irreflexive. As soon as you have one of these ordered pairs of 1, 1, you're not irreflexive. Typically, in your relation, you cannot be both reflexive as well as irreflexive. However, there are a couple of relations that can be both, okay? They are very rare. As soon as you have these ordered pairs involved like this, you typically, it's often one or the other, but that's not the only thing that can happen. So here, let's do the reason of why this is a no. No, because we actually had the ordered pair 1, 1 in our relation. And it didn't even matter that we also had the ordered pairs of 2, 2, 3, 3, and 4, 4. As soon as you had that first ordered pair of 1, 1, you weren't going to be irreflexive because irreflexive says none of those doubled up ordered pairs. Okay. So second example, and the second example is also on the building set 1 through 4. And for this guy, it's written not in terms of all of the ordered pairs explicitly listed out. It's written in terms of a formula. Now, for a relation that's this tiny, it's probably just as easy to go ahead and just write out the ordered pairs like what we did up top here. But I on purpose put it in this format because if you have a larger relation, say you have something like 50 ordered pairs you need to worry about, you typically aren't going to write out all 50 of those ordered pairs. But for this case, let's go ahead and actually write out what these ordered pairs are. So if you started with a 1, what could be the second position in the ordered pairs that start with 1? Notice here the first position must be less than the second position. So anybody have a guess on what the numbers could be here in this second position? Feel free to list all of them that are possible at once. And remember, they're all pulling from this building set A. So from the integers 1 through 4, which one are bigger than 1? Is the other way to read this. Yeah, so that we could have 2, we could have 3, or we could have 4. And then you do the same thing if you started with a 2. So here, the first position has to be smaller than the second position. So you look at your building set, who's bigger than 2? So what do you guys think? Who's bigger than 2? What should I write down over here? Again, feel free to list out all of them together. Yep, so this would be 3 and 4. So 2, 3, and 2, 4. And we could also start with a 3. So if you started with a 3, you're looking in this building set of 1 through 4. Who's bigger than 3? Yep, and in this case, there's only the one option of the 3, 4. And we'll go ahead and close off our ordered pairs. So there's only 6 ordered pairs in this relation. Now, if we ask the exact same question as before, is this new relation, which technically we probably should have called something other than R. Actually, let me go in and do that. Typically, if you have a second relation, you would call it a different letter. If you started with R, the next ones would be S and T are the common ones. And so the question is, what do you guys think? Is this relation S reflexive? And then we'll ask the same question about irreflexive. So what do you guys think? Is the relation reflexive? Correct. So this guy is not reflexive, and why? So reflexive, you need to have all of your ordered pairs that were doubled up ones. So from our building set, we needed 1, 1, we needed the ordered pair 2, 2, we needed the ordered pair 3, 3, we needed the ordered pair 4, 4. And notice actually, as soon as you look for the ordered pair 1, 1 and it's missing, you can say no, it's not reflexive because the ordered pair 1, 1 is not in this relation. Now, to go to the second property, which is irreflexive, irreflexive says you're missing all of those ordered pairs of 1, 1, 2, 2, 3, 3, and 4, 4. So what do you guys think? Would this relation be the extreme case where it's missing all of the ordered pairs that are doubled up ordered pairs? Could we actually say that this relation has the property of being irreflexive? Or it's just irreflexive? Yeah, so this one, because it is missing all of those doubled up ordered pairs of the 1, 1 through 4, 4, would actually be a situation of irreflexive. These two are actually special cases of types of relations that Can you guys hear me now? Okay. I was just muttering about that these were common examples that we'll see in the future too, was the only thing that you would have missed based on when you guys said you couldn't hear me. Okay. So not super important. Aside notes. All right, so we looked at a case where we were reflexive and we looked at a case where we were irreflexive. So next thing is let's look at the next set of properties. And the next set of properties come in a group of 3 because they're all very closely related to each other. Okay. And they're all closely whoops, just a second. So the question is, you can't be both reflexive and irreflexive at the same time. And it turns out the answer to that is normally yes. There is, however, a special case where you actually can be both reflexive and irreflexive at the same time, but most of the time it's one or the other or neither is typically the 3 cases that you have, but there is one special time when you actually can be both at the same time. It's super, super, super rare. In fact, it's so rare that there's one relation that it works on. One family of relations that it works on. But most of the time, yeah, it would be one or the other. Or neither. So the next set of properties that we've got starts off with the symmetric property. So same thing with the reflexive and irreflexive properties. They were not the same property, but they were definitely in the same sort of family of properties. Same deal here. And we'll start off with the big named one, which is the symmetric property. So symmetric property says you've got some relation R. It's on some building set A. Please note both the ordered pairs, the first and the second coordinate, would be coming from set A. And this relation is considered symmetric or has the symmetric property if every time that you have A related to B, that gives you or implies that you're going to be able to find B related to A also in the relation. Now, let's see what this would actually mean. Okay, so if we were dealing with the ordered pairs, so the proper relation itself, what would you have? If you were able to find the ordered pair A comma B, this would mean that somewhere else in that same relation, you could go and find your ordered pair B comma A. In other words, you have both ways of writing the ordered pair. Okay? Now, if you were in the digraph representation or the graphical representation, what this would mean is that in your picture, what you would be looking for is your doubled up arrows. Specifically, anytime you have one directed edge, you have to, between those same 2 endpoints, have the arrow that goes in the other direction. Now, here's the thing to watch out for. It is totally fine to have a vertex in the digraph where there's no edges between, but the only 2 options you have are doubled up edges or no edges. You're not allowed to have just one arrow between 2 different vertices. That's the thing that symmetric property is excluding. Now, in the matrix, this is where you have to know a little bit about linear algebra. The symmetric property tells you that if you take the transpose of your matrix, you will get back the original matrix. Now, because I'm not assuming that all of you have had linear algebra, and several of you said that you didn't, to the side here, let me tell you what transpose is. So if A, so transpose. And I'll do it not in a Boolean matrix, not in a matrix of just ones and zeros, so it's easier to see what's going on. So suppose A is this guy, A, B, C, D, E, F. And I on purpose made this guy not a square matrix. In this case, with a symmetric matrix, you are always going to start off with a square matrix because you're built on the same two building sets. And it would always be a Boolean matrix. In other words, all the entries would be ones and zeros. So when you're looking at it closely, there's a lot of things that look very similar. This one on purpose, I made everything look different. Okay? The transpose of a matrix is where you reverse the role of the rows and the columns. So here we have row 1. So row 1 is A, B, and C. And notice while I read out row 1, I rewrote row 1 to be a column. So what happens is your rows and your columns reverse. So in the original matrix, we then had a second row, which was D, E, F. That second row will now turn into a second column of D, E, F. And typically your original matrix and your transpose are not the same, because notice in that little example to the side, that illustrating example, the matrix sizes, they're completely a different shape. They're different size matrices, so they can't be equal to each other. The only time a transpose could ever be equal to its original guy is if the number of rows and the number of columns are the same, and that's when the shape of the matrix looks square. These guys are actually called symmetric matrices. It's not a coincidence there. So if you did take linear algebra and you remember hearing anything about symmetric matrices, same deal if you're looking in the matrix representation of the relation. If you didn't have any of that stuff, it's probably easier to spot this in the actual relation itself, or honestly, I think it's easiest to spot it in the graphical representation of the matrix. Okay. Second property, similar to symmetry, but not really the same, is something called asymmetric. This is the property that's not in your textbook. I'm going to put a bullet point there to the side, not because it's any more important or less important than the other ones, but just because it's not in your book. Okay. So asymmetric, a relation R on some building set A, again, it's only one building set, so we're looking at relations that are subsets of A cross A, is considered to be asymmetric if, why did you guys not fly in? All right, I'm going to have to cross these guys off. If A is related to B implies the reverse is not true, and you're not allowed to have any loops. Okay? So in terms of what this says is in the relation, if you have A comma B in your ordered pairs, and that's in your relation, you will not have the reverse. So of those two copies, exactly one of them is in your relation, and it's irreflexive. If you look in your digraph, this is the situation where you either have this two vertices have no arrows, no directed edges between them at all, like between A and C, or you have exactly one arrow between two vertices, like A and B. And key thing here is no loops. Now, in the matrix, here's what happens. Along that diagonal, you're going to get all zeros. So that's the irreflexive part. So all zeros there. But over here, say you have a 1 right here in this position, row 1, column 2. In the corresponding position, sort of the mirror image of that position across the diagonal of zeros, you're going to have the opposite. So what happens is anywhere you have a 1 in the matrix, if you folded the matrix along this diagonal right here, every position where that 1 touches on the other side of this diagonal has to be a 0. It's okay if there's 2 zeros across the way, but for any 1, it has to actually be a 1 over there as well. You can actually do this same sort of thing up with symmetry, but in symmetry it changes. The diagonal doesn't matter. 1 zeros, 1 zeros, whatever you want in there is totally fine. But here, if you have a 1 in the position, you have to have across the diagonal, you have to have a corresponding 1. So one is you have both parts, got both of your ordered pairs. The other one is one, at most one of your ordered pairs. Okay. So that's asymmetry. I personally think it's easiest to say no two-way arrows, no loops. And the last property is antisymmetry. Both the prefix here of a and anti, both refer to not. So there are 2 types of not being symmetric. Now for antisymmetry, in the ordered pairs, if you have AB is in the relation, then BA is not in the relation. In the digraph, if you have A and B, and there's going to be an edge or a relationship between them, there's only one of them. But here's the difference between antisymmetry and asymmetry. Antisymmetry, loops are okay. We don't care one way or the other. In terms of the matrix, it looks very, very similar to the matrix up top, except the stuff on the diagonals, we don't care. Okay? So one way to think about this is, so note, and this is probably why your book doesn't have asymmetry in it. Asymmetry is antisymmetry plus the irreflexive property. It's like merging the 2 properties together. Okay? Where both the symmetric property up here at the top and the asymmetric property here at the bottom, both of these guys, nobody cares if you have loops, don't have loops, all loops, no loops, some combination thereof. The asymmetric is you're not allowed to have any of the loops. So that's the big difference. Some people like to actually switch this order and do check if when they're checking properties, check the symmetric property first, then the antisymmetric property, and then the asymmetric property after the antisymmetric property, because if you're not antisymmetric, there's no way you're going to be asymmetric. But let us look at an example. Did I actually go to the right example? Yeah, all right, we're good. So for this example right here, suppose you have your buildings 1, 2, 3, 4, so similar to what we've had in the past. And suppose we have these ordered pairs of 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 3, 3, 4, 4, 3, and 4, 4. And we're going to check the 5 properties that we have so far. And I'll just go ahead and throw them up there. So if we look at this, stop touching that. Finger, stop. Moving that thing away. All right, so we have these 5 properties. If we look at this particular relation and we want to see if it's reflexive, what do you guys think? Is this guy reflexive? And what you saw is it also turned up on a poll everywhere thing. So if you guys wanted to go ahead and look at this quicker than what we're talking it through, you can actually go into poll everywhere right now and check to see if you think it is reflexive, irreflexive, asymmetric, or antisymmetric. You guys should be fine to do the reflexive and irreflexive on your own right now, but I wanted to talk through the symmetric, asymmetric, and antisymmetric together. Okay. So actually, since I said that, let me jump down to the symmetric prop. We'll go ahead. Reflexive. We guys had a guess here that it should be reflexive. I see about a third of you have made a guess that it should be, have started making guesses. And so in terms of this, if we're looking for reflexive, what is it that we're actually looking for? So we want all of the ordered pairs in the relation for all of those building elements from our set A. Okay. Yep, we want all those ordered pairs 1, 1, 2, 2, 3, 3, and 4, 4. So, yep, we are reflexive. And I'm just going to put a check mark there because that's easy. Okay. Now, if we're then looking at irreflexive, what do you guys think? Could this guy be irreflexive? And let me write down irreflexive here, since unlike on a board, it is not put up there to the side where you can still see it. Right, so this one, the answer would be no. And the answer would be no because you have one of those ordered pairs already. Now, here's one of the reasons why I want to do this together. We can do the rest of these properties in the ordered pairs as well, but it's actually easier if you draw the graph. So if we draw the digraph associated with this relation, we've got 1, 2, 3, and 4, and let's put all these bits and pieces together. So the ordered pair 1, 1 would be a loop at 1. Ordered pair 1 to 2 would just be 1 to 2. Ordered pair 2 to 1 would be 2 back to 1. Ordered pair, where did you go, cursor? Ordered pair 2, 2 would be the loop at 2. Ordered pair 3, 1 would be an edge starting at 3 going into 1. 3, 3 would be a loop at 3. 3, 4, start at 3, go to 4. 4, 3, start at 4, go back to 3. And where'd it go? 4, 4, a loop at 4. Do a quick double check, make sure I drew that digraph correctly. I'm not seeing any missing edges, at least so far. All right, now notice reflexive, super easy to see. We got loops on all the vertices. Irreflexive, we've got at least one loop, so not irreflexive. What do you guys think about symmetric? Or maybe I should throw this up into the poll everywhere. That way you guys have a guess here. Ooh, I do have different guesses. So let me actually pause from writing this down. So I see that some of you have made a guess here. So how about the rest of you make some guesses? You should be able to select all that apply. We already gave you the answers for reflexive and irreflexive, okay? So now it's see what you think about the symmetric, the asymmetric, and the antisymmetric. And we had the graph up here just a second ago. So I can only choose one. Let me fix that then. Just a second. You're right, you can only choose one. I'm going to fix that to, all right, 5, so you can select as many of those guys as you want. All right, you should be able to change it now. Yep. All right, so I'm going to jump back to the digraph so you can see the digraph just because I think that's helpful for us. Well, I can't find my cursor now. And then we'll come back to that answer. Okay. While you guys are doing this, or while you guys are thinking, I'm going to go and write what we look for symmetric, asymmetric, and antisymmetric. This is the same definition as before, it wasn't visible on the screen, so I wanted you guys to see it. All right, there's a few more choices. It looks like we've stabilized in choices too. All right, so going back, let's see. I'm going to show what you guys guessed. All right, so according to these guesses, Your guesses were pretty spot on here in terms of reflexive and irreflexive because we literally already did them. In terms of symmetric, asymmetric, and antisymmetric, I see that nobody checked asymmetric. That's good because we had loops. So now we're really just checking, do we think it's antisymmetric or symmetric? All right, so let's actually check to see what we had here. Okay. So for antisymmetric, this is a big fat no, and that is because we had that single, we have at least one loop, and that can kill asymmetric right there. Now, in terms of symmetric, what do you need? The loops don't matter, but anytime you have one edge between two vertices, you have to have both directions. In here in the ordered pairs, we've got 1, 2, and 2, 1, so that would be the two parts that we need for the ordered pairs. But if we look in the diagram, are all the connections between two vertices two-way connections? Arrows. Look for the arrows. So do we have arrows in both directions for all of our connections between two different vertices? Notice we only have 3 connections between two different vertices. 1 and 2, yep, both ways. 3 and 4, yep, both ways. But what about 1 and 3? Do we have both directions between 1 and 3? We don't actually. So if you have even one connection that has only one direction of your arrow, that means you're not symmetric. So this one here is no, because we don't have 1, 3 in our graph, but we do have 3, 1, I shouldn't have said graph, in our relation. Okay? You don't. So for the ones that have no connections whatsoever, remember this is an if statement. So if you have a connection between 1 and 4, we don't, so it's automatically true. Same deal here, no connection whatsoever, so this if statement is automatically true. The only time you actually have to check this is if you have at least one of the arrows between your two vertices, between your two numbers. That's when the symmetry property actually comes into play, and this is supposed to work in all of those cases. That's the key thing. All of your different connections, two-way connections. Now, last property, what do you think about the antisymmetric? So this one, you actually approach it the same way you would the symmetry property, so this symmetric property. You look at all of your connections between two different vertices, and all of these connections have to be what? If there's a connection, there's only one of them. So if we look between 1 and 3, there's the only one of them connection. So that's perfect. But if you look between, say, 3 and 4, what happens? Do you have only one arrow between 3 and 4? No. What does that tell you about antisymmetry? Do we have the antisymmetric property for this particular relation? Right, so you wouldn't have this property because not all of these connections are single arrows, so this one also is a no-go, and that's probably why I didn't notice that you guys couldn't select more than one property before, because this particular example, we've only got the reflexive property, because here we have both 3, 4 and 4, 3 in your relation. Key thing about symmetry, asymmetry, and antisymmetry is in your connections between two different vertices, it's an all or none. Symmetry, all the connections have to be two-way or no connection whatsoever. Asymmetry, all the connections have to be a single arrow or none. Antisymmetry, all the connections have to be a single arrow or none. And the only difference between asymmetric and antisymmetric is if you look at the loops or not. Okay? So that's the crash course on the first 5 properties. We are crazy over time. I'm so sorry about that. So next time we'll pick up the 6th and last property, and then we'll look at, well, if different relations have some of these properties, they then get special names. And we should wrap up what we'll talk about in terms of relations on Friday. Although, to be fair, the rest of our topics in this course are built off of relations. It's just then special types of relations. Okay? So I will hang out for a little bit if you guys